The current research discusses the development of dual EPO nanoparticles for the treatment of peripheral arterial disease. PAD is a condition caused by the narrowing of the arteries from atherosclerosis in the lower limbs. PAD patients with critical limb ischemia have a high mortality rate and morbidity rate and affects approximately 8 million Americans. Since current invasive treatments for PAD have many complications and disadvantages, developing innovative approaches to overcome these limitations is on demand and critical. Therefore, we propose a non-invasive and promising polymer as a nanocarrier to control proangiogenic vector and its gene to ischemic tissue to treat PAD. Erythropoietin can stimulate endothelial cells proliferation, migration, and protection from hypoxic environments and promote vascularization. We are using an FDA-approved polymer as a dual carrier to deliver both EPO protein and EPO circular DNA to release sustained EPO for PAD long-term treatment. The experimental test plan consists of AIM-1, which is the fabrication, optimization, and characterization of EPO-C DNA-loaded nanoparticles, EPO protein-loaded nanoparticles, and EPO protein and EPO-C DNA-loaded nanoparticles. AIM-2 is the in vitro studies to evaluate the therapeutic effects of the fabricated nanoparticles. The process began with plasma purification, in which engineered E. coli bacteria containing EPO-C DNA are grown in LB broth with the selected antibiotic ampicillin at 37 degrees Celsius. EPO plasmid was purified and collected using the coagent endo-free plasma purification. Plasma transfixion was done using the lipofectamine 3000 reagent and was conducted to confirm the function of EPO plasmid on Lenti-X cells. Nanoparticles were then fabricated using the double emulsion method to load purified plasmids and EPO protein. After solvent evaporation and lyophilization, the size and polydispersity of nanoparticles were quantified using the dynamic light scattering machine. In vitro testing was done using nanoparticles on endothelial progenitor cells. EPCs were exposed to different concentrations of nanoparticles to measure cell proliferation at low serum conditions. A protection study is performed under a stress-induced condition of 550 micromoles of H2O2 to mimic PAD pathology. Cell viability is then quantified using the MTS assays. EPCs pre-exposed to nanoparticles are used for studying the therapeutic effects on the cell wound healing by scratch assay using a pipette tip and then measuring after 16 hours. An echofluorescence microscope was used to obtain the initial and final wound distances. An EPC transmigration study was performed using the 24-well transwell system, and after 12 hours, non-migrated cells were removed at the upper side of the membrane, while migrated cells at the lower side were fixed and the nuclei stained. After imaging, the number of cells were quantified using ImageJ. In Table 1 of the experimental results, we see the characterization of nanoparticles, in which the average size of the nanoparticles ranged from 147 nanometers to 265 nanometers, and the PDI ranged from 0.161 to 0.266. Figure 1 shows us the cell transfection using purified EPO-C DNA at day 1, day 2, and day 3. Figure 2 shows us the EPC proliferation study of EPO-C DNA nanoparticles. The results show EPO-C DNA nanoparticles can promote cell growth at low serum conditions. Figure 3 shows us the EPC protection study after 1 day of H2O2 treatment. The results demonstrated that EPO-C DNA nanoparticles significantly protect cells under stress conditions. Figure 4 shows us the scratch assay of EPO-C DNA nanoparticles at 0 hours and after 16 hours. Figure A shows the representative animated images before and after cell migration, and B shows us the data analysis of the experiment. Figure 5 shows us the transwell system of EPO-C DNA nanoparticles on EPC cells. The bar graph shows the cell migration between no treatment and EPO-C DNA nanoparticles, and Figure B shows us the representative images at 4 times magnification. The transfection study confirmed the EPO-C DNA plasmid function and transfected Lenti-X cells expressed in cherry fluorescence protein after 1 day, having the highest transfection efficiency and highest intensity at day 3. Fabrication of the nanoparticles were successful and had an acceptable range of PDI and size. They were both confirmed using the DLS. Proliferation and protection studies of the EPO-C DNA nanoparticles show that they can prevent cell apoptosis by 1.8 times compared to the no treatment group in the presence of the ROS compound, and they outperformed free EPO and plasmid EPO nanoparticles and EPO-C DNA PDA nanoparticles. EPO-C DNA nanoparticles continue to stimulate cell growth until day 7. cDNA nanoparticles in the migration study show that they can boost cell migration via the Scratch-Assay and Transwell study by 3-folds and 7-folds respectively compared to the no treatment group. cDNA nanoparticles were successfully synthesized to induce therapeutic effects on EPCs. In vitro studies show that the formulated nanoparticles can promote growth, regeneration, protection, and migration of PAD ischemic cells. More in vitro studies will be conducted to verify angiogenesis of cDNA nanoparticles, and in vivo studies will be performed to investigate the promising effect of nanoparticles on PAD mice.